In this echo chamber at the Building Research Station at Watford, the sound of a gunshot takes about 20 seconds to die away. The surfaces are hard and opposite walls are not quite parallel to each other. How does the sound travel from one wall to another? Does it travel as a wave? And if so, how can we tell? Let's start with a familiar object, a loudspeaker, producing a simple sound. Is it moving? Some things move so fast that we can't see. Yes, it's moving all right. One way we can see this is to use a stroboscope and make it move in slow motion. One like this. Another way is to take a high-speed cine shot and then to slow it down. You might like to think why both methods give us the same effect of slow motion. We took a high-speed film of this loudspeaker vibrating at a frequency of about 50 cycles a second. Here is a view from the back of the loudspeaker. It moves like a piston. And here is a close-up of the front edge of the speaker. This loudspeaker is also giving a note of about 200 cycles a second now, a fairly low note. With a simple control, I can raise the frequency. Until now, it's about 1,000 cycles a second. Let's go back to a very low frequency. I spoke about the loudspeaker vibrating, but we prefer to use the word oscillating. The cone of the loudspeaker is now oscillating at about 26 cycles per second. What is the air doing? Air is the medium surrounding this loudspeaker through which the sound must travel or be transmitted. Does the air move in a steady stream, as it does in a wind, or is there some sort of pulse or wave which sends the sound along? Each part of the medium moves back and forth, but the medium itself doesn't travel along with the wave. You can see that clearly in the slinky, first at normal speed, and now in slow motion. Second, each part of the medium moves back and forth just a little later than the part before. And the wave machine shows this clearly. Third, energy travels with the wave. Let's see if any of these apply to sound waves. Air is the medium round the loudspeaker, but we cannot see it. However, a candle burning in the air can help us. When I switch the loudspeaker on, the candle is obviously affected. But here there are many drafts, and so we shielded the flame and again used the cine camera as a stroboscope to slow the motion down. We placed the candle and speaker in front of a cine camera running at a slightly different frequency. The flame and the speaker cone, shown by the white mark, are clearly moving from side to side together. Here is the flame by itself, in fact moving back and forth about 26 times a second. The flame from above appears rather like a dot on our wave machine. Except that there, each dot went up and down. This is rather odd. The loudspeaker moves in and out, and the candle in the surrounding medium air, carrying the loudspeaker's sound, seemed to go with it. It's difficult to see how this idea we have of a wave, with the medium moving at right angles to the direction of the wave, can explain our loudspeaker experiment. Perhaps our trolleys can help. Imagine these two trolleys to represent air particles. I haven't joined them together with springs because air particles move about much more freely. This is the outline of the loudspeaker. And when it oscillates, the candle flame, and so presumably the air, moves in this direction. And it's somehow squeezed together. This is rather like the air in a bicycle pump, which is squeezed. Air is springy and resists being compressed. Perhaps sound can be transmitted and explained in this way. Here's a model of how a sound wave might travel. Assume that the loudspeaker is still vibrating. We've arranged the trolleys in a line ahead to be rather like the air particles in front of the loudspeaker. And as the wave travels down to the end and back, you can see each trolley moves back and forth very much like the candle flame. The air particles are not connected together, but they can push each other with these springs. So now we have two kinds of wave motion. In the first kind, the parts of the medium move back and forth at right angles to the direction of the wave. This is called a transverse wave. Water waves, and those on our machine, move like this. In the second kind, of which sound waves are an example, the parts of the medium move back and forth in the same direction as the wave, and this is called a longitudinal wave. Here is a method you might like to try for measuring the speed of sound waves, which are longitudinal. The source of sound is metal hitting metal. Here's one boy with a stopwatch, and there are 4 others as a check. Rulers are put down starting from the source of sound. The rulers help the boys to get a regular length of pace, and the distance from the source to the wall is then paced out. Notice that the boy producing the sound keeps the original sound and the echo in step. Meanwhile, the timekeepers measure the time taken by a certain number of outward and inward journeys of the sound. Knowing the distance of the sound's journey and the time taken, we can then calculate its speed. If you don't already know the value of this speed, I'd like you to find it out or measure it for yourselves. And now, what about the question of energy? You will remember how earlier the movement of the loudspeaker affected a candle flame. Some energy was transferred. In this experiment, a speaker is placed at one end of the long box and a candle flame at the other. When the speaker is turned on, enough energy is produced to blow the candle out. So energy travels with a sound wave, and we can concentrate this energy, as we can with light energy, by using a lens of some sort. Here is one. This is a balloon filled with a gas which is not air. With a microphone here and a loudspeaker there, you should be able to hear the sound. But first we'll have to switch off the microphone above and just use this microphone. Listen while I move the balloon up and down. Did you notice that the sound is concentrated or focused by the balloon? Well, here's a rather difficult question for you, which you can take down at the end of the program. Was the gas in the balloon more or less dense than air? It's difficult to do these experiments in a normal room or even in a large studio like this because there are all sorts of disturbances, especially from echoes. So we took our cameras to another chamber at the building research station, which has quite opposite properties to the one we saw at the beginning of the program. The walls, ceiling and floor of this room are covered with foam polyurethane wedges, 4 feet long. There are 22,000 of them. When the door is closed, nearly all of the sound in the room is absorbed, and there is an eerie silence. This is a particularly good place to carry out our sound experiments because of the lack of echo. It is called an anechoic chamber, and this one is the largest in Europe. Its primary use is in the study of sound transmission through various materials used in the construction of buildings. The same gun we used before, fired in this chamber, is very unimpressive. Because of the wedges on the floor, a working floor of wire mesh is stretched across the chamber, 2 feet above the floor wedges. Now for the experiment. You will all have noticed in your own sitting rooms that sound is not, as we say, very directional. In fact, you can sit anywhere and still hear the program coming from your radio set. Sound seems to spill out in all directions. For example, sound from this loudspeaker is heard not only here, but here and round here. We investigated this property in the anechoic chamber, first by moving a microphone in front of a large loudspeaker. Notice that we pick up most sound straight ahead, and less either side of the center line. On the other hand, if we narrow down the width of the sound source, it is quieter straight ahead, as we should expect. But the sound doesn't seem to fall off as much on either side. Perhaps this is not so expected. So, narrowing down the slit makes the sound quieter, which is not surprising, but it also makes it spread out more in all directions, and perhaps this is more surprising. Does this fit in with our idea of sound as a wave motion? If you haven't already done so, I'd like you to compare the effect of water waves going through wide slits and then on this ripple tank we narrow the slit down to make a narrow one. We refer to this spreading out of waves as diffraction. And the fact that sound waves spread out round corners is strong evidence for the fact that they are wave motions. Let's experiment a little more. Some of you may have tried using 2 sources in a ripple tank to produce this sort of pattern. Would we get a similar effect using 2 loudspeakers? We tried in the anechoic chamber. The right-hand speaker is on all the time, and the microphone is in front of and between the speakers. Notice what happens when we switch on the left-hand speaker. The volume increases. That's expected. Now move the microphone to one side and switch on the second speaker again. Now the volume decreases. That seems more surprising. If we now look at the speakers from behind and pass a microphone across in front of them, this happens. In this experiment with two loudspeakers, we were only considering what happens in one line. What do you think happens here and here? Well, here's an experiment you can try for yourselves to find out. Set up two loudspeakers in the school playing field and connect them to the same oscillator. Switch on the two speakers, both at the same frequency of about 1,000 cycles per second. A group of listeners standing in front of the speakers moves back and forth until the sound seems to be at a maximum. Any one person will hear the volume of the note rise and fall as he moves. At first, we seem to have just a disorganized crowd. But eventually, a pattern like this forms, an interference pattern. You may think the pattern you just saw and the ripple tank pattern are very different. But each is part of this pattern, which would be obtained if, for example, the loudspeakers could send out their sounds in all directions. And now I hope you've got a pencil and paper ready. First, what is the speed of sound? Second, was the gas in the balloon more or less dense than air? And here's a third question for you. Do high notes and low notes spread out equally when they pass through slits? You can try this with them going around corners as well. You might like to try that one out practically using, say, a drum and a whistle, like this.